Okay, someone cool. This is part 2.3 NEC 671. Our topic is on steady and level cruising flight. And we start with the revision of thrust required and power required equation. So the first thing we see here is the free body diagram of an aircraft uh, flying at a steady and almost level. Okay, cruising flight. Why I say almost level? Because it has some shallow climb. Okay, it's not like it's climbing, but I exaggerated the angle. Okay, because the angle actually is small. So it is flying at trajectory angle gamma. Okay, which is basically very shallow. Okay, maybe less than 10 degrees, something like that. Okay, and it's also flying at angle of attack alpha. So this axis, this is x wind axis. Okay, this is inertia or the earth axis, and this is the body axis. Okay, so the overall attitude of the plane is theta or the pitch. Okay, the pitch angle. Okay, so because you know that the pitch angle is basically an angle of between x body and x axis of the earth. All right. Um, the rest is all the forces on the plane. Okay, and the CG. We have lift, which is perpendicular to the wind axis, drag parallel to the wind axis, thrust parallel to the body axis, and mg weight, which is perpendicular to the earth axis, okay, which is basically straight in the z direction. Okay, since this angle is small, alpha is small, gamma is also small, we can assume them to be zero. Okay, almost zero. So in other words, the airplane now is the x body and x earth is basically overlapping each other, including the wind axis also. So since these two angles are small and theta is also zero, then thrust is basically is directed towards the x-axis, drag is the opposite of it, and lift is opposite of the z-axis of Earth, and mg is okay. So it's clear. So first thing you have to look at the aerodynamics of the plane, because the thing is you need to calculate the CL, okay, of the plane, because the CL is a function of angle of attack. So dCl d alpha is basically the change of lift coefficient over the change of angle of attack, and CL naught is the lift at zero angle of attack. So this CL, okay, so for each and every angle of attack, you need to determine the CL of, okay, so that when you know the CL, okay, when you know the CL, you know what is the cruising speed, okay, at that particular angle of attack. So there's only one cruising speed at one angle of attack. I think we have covered this before this. Okay, second is the drag coefficient, CD, okay, because basically CD is KCL squared plus CD naught. Okay, K is 1 over pi E aspect ratio. Pi is pi, E also efficiency. Aspect ratio is aspect ratio of the wing of the plane. And CD naught is a drag coefficient at zero lift or parasite drag. Okay, now let's start with equation of motion. Since this aircraft is flying steady meaning that there is no acceleration at level, okay, zero angle, okay, zero pitch angle. So the acceleration in x and z direction is zero. Okay, level means at the same altitude. Okay, constant altitude. Okay, steady means no acceleration, forward acceleration. So the acceleration in x and z is zero. Okay, so in z direction, okay, in z direction, we have weight and lift. Okay, so weight minus lift is zero. Okay, because the acceleration in z direction is zero, meaning that at this condition, if you move the L to the right side, then your lift is equal to weight. Okay, and we know that lift is half v squared as CL. Okay, I think I tinggal rho here. Okay, you should have a rho here. Yeah, I can just add rho, no problem. Insert symbol. Oh yeah, that's in the easy way. Yes. So I'm just gonna copy the row here. Paste. Paste. Upright. Okay. So length is half rho v squared SCL, and in x direction we have truss and drag. Okay. So truss positive, drag is negative. Truss minus drag is equal to 0, and truss is equal to drag. So basically, the truss available in this aircraft, okay, for zero acceleration will be equal to the drag. Okay, the drag. So basically, it's a truss. So for steady flight, okay, no acceleration, the thrust required by the plane must be equal to the drag. And drag is half rho v squared SCD. Okay, when you get the CD here, it's from aerodynamics. When you get the CL, it's also from aerodynamics. Okay, so that is thrust required. So I highlighted here the thrust required. Okay, now I use TR is equal to drag. So meaning that you have to stick in your mind that drag is the thrust required of the plane. Okay. Now there is also power required. Okay. Power required. Okay. There is double. Okay. Is half rho v q SCD. It is basically the drag times velocity of the plane. Okay. The airspeed of the plane. So that is power required. So basically, a power required is drag times velocity. Alright. Now, the plot of drag or thrust required versus airspeed. Okay, this is the most important plot for cruising analysis. It tells everything here. Okay, many things. Now, this is the plot. Okay, and this plot is called the thrust required or drag. Okay, this is drag of the plane. Okay, in Newton or in pound. Okay. So it is actually affected by two factors. One is from the induced drag, another one is from the palisade drag. Okay, if you look at now on the left, the CD equal to KCL squared plus CD naught. Now KCL squared is induced drag, CD naught is palisade drag. So if you look at KCL squared, okay, as you increase the airspeed, the CL is reduced. Okay, as you increase the airspeed, the CL is reduced, and the CL here is squared. So KCL squared is definitely getting smaller and smaller and smaller. Okay, as you increase the airspeed, although the airspeed is increased. Okay, although the airspeed is increased, the overall induced drag will surely decrease. Okay, as you increase the airspeed because of this CL squared. Now, how do we determine the CL squared? For velocity, we use this equation of lift. Okay. Now that lift is equal to weight, so we replace here with weight. W weight is half rho v squared SCL. So as CL is decreased, okay, and the weight is constant now. Okay, the weight is constant. Okay, so as CL is decreased, the velocity as we increase the velocity v squared, weight is constant, CL is definitely going to be decreased. So when CL is decreased, induced drag, okay, KCL squared will definitely decrease. Okay, I will prove. You have to prove it. Okay, and as for CD naught, it is constant. So at any airspeed, the CD naught will be the same. So as you increase the airspeed, of course, the CD, the total drag or the total thrust required will also be increase. Okay, I'm going to stop here. Continue after this.